Today I'll be talking about equity, which is a deep learning-based metric for detecting, characterizing, and mitigating dataset bias. So let's look at how biases occur in healthcare. We have systemic biases, which is translated into dataset bias. Dataset biases become translated into models when models are trained on biased datasets, and these model biases can propagate into the system. There are already methods to focus on model biases, such as model retraining via prospective validation and model calibration, and there are methods that focus on systemic biases, such as grassroots interventions like anti-racist policies and patient-provider education. What equity focuses on is this core principle of garbage in, garbage out. This means that equity will focus on detecting biases at the dataset level and then suggesting additional bias mitigation measures such as collecting relevant data and selecting more informative outcomes in order to mitigate these biases before model training even occurs. So the core principle of equity is that you have this multiracial or multi-group dataset, and you can calculate the AEQ value at each group and each label. You can intervene on this dataset either by collecting more relevant samples or changing the outcome to become more informative, and this will ultimately lead to a decrease in the discrepancy in test metrics between groups. So we focus on the Obermeyer paper, which was published in Science, and they learned that racial bias in cost-predictive algorithms can propagate systemic forms of inequity in healthcare resource allocation. When using cost as a risk-derived metric, Black patients at a given risk score were considerably sicker than their white counterparts. This bias arises because the algorithm predicts healthcare costs rather than illness, but unequal access to care results in far less money being spent on care for Black patients, even when they're significantly sicker. And so the core problem is, should we select comorbidity score or should we select total cost? And they determined when switching from a cost-based metric to one that uses comorbidities, the algorithm was able to mitigate some of these biases. So let's focus on how AEQ can actually replicate some of these results at a much smaller sample size. So AEQ works by focusing on the learnability of a dataset. If a dataset has fewer informative features and is more homogeneous, it will have a lower AEQ versus a dataset that is heterogeneous and has more informative features. In the case of sampling bias, an underrepresented group will have a higher AEQ. In the case of complexity bias, a more complex group will have a higher AEQ. In the case of label bias, both groups will have the same AEQ value. So let's actually apply this to the dataset. So if we look at the Obermeyer dataset, we can actually see that there are a bunch of different demographic variables, as well as comorbidity variables, such as alcohol and anemia, triglycerides, as well as medications, such as Lasix. Then we see the three outcome variables here. We'll be focusing on log cost, and we'll be comparing that to Gagny score, which is a measure of comorbidities. So in order to measure biases, you need to install these requirements, such as sklearn, Torch, SciPy, Torch Vision Pandas, as well as the CNN MCSE library. We can import the measure disparity function from the CNN MCSE library, and the three key inputs that we need are the dataset path here, the demographics column, and the outcome columns. When we actually measure the disparity, it takes 7 minutes, and if we add a GPU, it will take even shorter. The output is a table with the mean and standard deviation for each group outcome and risk. So let's interpret this. Let's focus primarily on the log cost. We see that the AEQ value for Black patients is significantly higher than the AEQ value for white patients. This means that it's harder to generalize for Black patients than it is for white patients. Second, if we look at the joint AEQ value, it's higher than both of them combined, which means that there's a form of bias here because they belong to different distributions. Second, if we focus on the outcome of Gagny score, we actually see the AEQ values are relatively equal, which means that it'll be relatively equal amounts of ability to generalize between different groups. Second, we see that the joint is smaller than both of these. This means that they belong to similar distributions and that training on both will actually improve generalization performance. So now we mitigate these biases, we focus on those interventions that we mentioned above, and we can actually see that the AUC on Black patients will increase by 0.1 if we conduct these interventions, which is very high with a very small standard deviation. If we look at other fairness metrics such as false negative rate, which is a measure of underdiagnosis bias, and precision, which is a measure of how efficient we're actually allocating our resources, we can see that both the precision goes up and their false negative rate decreases. In summary, we've showed a very elementary demonstration of how our method works, and while we show that our method works on simple linear models in this example, we know that it also works with complex models such as deep convolutional neural networks and intersectional identities.